Welcome to part 4 of the Quant Trading Accelerator. In this video, it's all about the time series. In the previous videos, we've been building up to this video. We focused on arrays, and then we looked at vectors, and now we're looking at the time series. So the goal of this video is to get some basic statistics for analyzing time series. We're also going to look at some time series fundamentals, and then once we've got a good foundation in time series, then we're going to use some econometrics to model the fundamental trading dynamics. And this is why I believe econometrics is a very good foundation for quantitative trading, because it allows you to model these two fundamental dynamics. So we're going to start off with statistics. So I'm going to write this down here. And the most important measure is for central tendency. And there are two common measures. And the first one is the mean. I'm going to put this here as well. And the mean, so let's just have an example. So with the mean, I'm just going to import NumPy, and I'm going to create a time series of trade P&L. So each element represents an individual trade. So for example, here we're going to have, so first trade made $10, second trade made 11, and we're just going to get a few, right? And then we're going to do this minus 400, $2, $10, $11, $11, $8, $10, 10.2. Okay, and we're going to take the mean of this. And this basically tells us what's the expected value of each trade. So we see here that it's a negative number, right? The only caveat of the mean is it's sensitive to outliers, and I'm going to show you an example, right? So now we're going to look at another measure of central tendency, which is the median. And this basically looks like, okay, what's the middle number essentially? And we're going to just look at the code for this. Is now if we just use NumPy to calculate the median for trade P&L. And you can see here, this is why I chose this, because the median is a positive number, but then the mean is a negative number. So the reason for this is that the median is not sensitive to outliers. It just finds what's literally the middle number when you sort it and take the middle number. Whereas the mean is calculated differently. So it's more sensitive to outliers, and you either want to use the mean or the median depending on if you want to factor in outliers or not. So that's the two most common measures for central tendency. And now we need to measure the spread or the dispersion. I'm going to put both spread and dispersion. How far the values deviate from the measure of central tendency. Oops, let me just put this as a text. Okay, so, and the most common measure is the standard deviation. And I'm not going to go over the maths of it, so I really encourage you to actually just look at the maths of this and the algorithm behind it. But I just wanted to show you the practical applications of them. So for example, and this is the standard deviation, both these the central tendency and spread dispersion gives you a really good foundation. So for example, I've got two portfolios. Let's say portfolio A, and let's just say it makes $1 and again, this is a time series, and I'm just going to get some numbers here. Actually, I'm going to copy and paste it a bit quicker. Okay, so here's portfolio A, and if we look at these are trades, okay, and we look at, if we sum them up, we'll see the portfolio A. Okay, so it's made $6, and if we look at the standard deviation, which measures how actually we look at the mean of it as well. So if we look at the mean of this portfolio A, okay, so it's 0.6, and if we now look at the standard deviation of portfolio A, so here the deviation is around 80 cents, so that's the measure of dispersion from the central tendency. But we're going to look at if this doesn't make too much sense, don't worry, because it should make more sense once we further in the video. So now what I'm going to do is, and I'm just going to give you an exactly same portfolio, like a different portfolio, but they both add up. If you add up the values here, that they all add up to 6 as well. But you'll notice that these values look kind of like extreme. So now if we measure the standard deviation for portfolio B, you see here that it's a much higher number. So this tells us that there's a higher spread of numbers from the central tendency. And this sort of makes sense, because if you look at the values here, these values are sort of deviate quite strongly away from the central tendency, whereas like here the values don't really fluctuate too much, whereas here the numbers are more volatile, right? So this is what it is measuring. And with this, just the mean and the standard deviation, you can calculate what's called risk-adjusted returns. Okay, so risk-adjusted, so what I'll do is now I'm going to introduce pandas. So pandas is a data analysis framework, is the most common one. We have been building sort of our own one, but it would just be too much code to write all the functionality. But you'll be able to be really comfortable by now working with pandas, because we've gone over vectors and vectorization and vector algebra and arrays. So now we're working with pandas. It should be really intuitive, like what we're doing, like behind the hood. So for example here, I'm going to just run this. So it's exactly the same data, but we're just now representing what's called a data frame. And a data frame is essentially a table. And you can see here, it's more visually, you can compare each element in the time series. So this is a time series for portfolio A, and this is a time series for portfolio B. And so now we've got it in a data frame. It just makes it a lot easier to calculate and benchmark each portfolio. So what I'm going to do now is I'm going to benchmark it. So I'm creating another data frame here, and it's called benchmark. And I'm now just going to run this. Don't know why it's taking so long. Okay, here we go. So essentially I've just calculated just the mean and the standard deviation. Okay, so you can see here that the portfolio A and B, we've calculated the total sum. So the total P&L, they both like earn $6. Just, it's a toy example. They both have the same central tendency. So they're both here it's 60 cents on average it makes. But here was the key distinguisher, which is the standard deviation. you see with portfolio A, it has a much lower standard deviation because the numbers, that the P&L values in the time series is less volatile. Whereas here, it's a much higher number because there's much higher deviations away from the central tendency, which is this measure here. So, and essentially, what we can do now is calculate what's called the Sharpe. So what we're going to do here now is do benchmark, and to add new columns into pandas, this is like the notation for it. So it's even, that's kind of smart that it knows what I want to do here. So now we're going to run this. You can see now. So this is what's called the Sharpe, and essentially the Sharpe just tells you it's a measure of the return over risk. And so we're quantifying the return as the average or the expected P&L, and then over the standard deviation of the P&L here. So you can see here that the Sharpe here is much higher than it is, like here, this is pretty much like 0, right? Whereas here it's a much higher value. Because the standard deviation is much lower. So this is a really good measure for measuring like how much risk you want to take and how much risk is being reduced. So the higher the Sharpe, the more stable and consistent your profits or returns are. So now we've got so that's just like the basics, some of the basic statistics. Another very important measure for a time series is the correlation. Okay, and the correlation is either positive or negative. So we just do pos cor. Okay, oops, maybe just put this text. Okay, so I'm just going to give you like an example here. So this is an example of like a positive correlation. So the correlation measures how, for example, two time series move together. Do they move like positively together or negatively together, or does, for example, if one time series goes up, the other one goes down? So this is like this is what it is essentially, how they move together. So for example here, if it's a positive correlation, this means that they move up together and move down together. And for example, you could even have here's like an example of like a perfect correlation, but in practice you never see a positive, like where it's 1.0. So the strongest correlation is either -1 or 1, but in practice you never see it, because in real world it's never as strong as this. So now we need to look into negative correlation. And also, again, I really encourage you to look at the maths of this. I'm not covering it in here. I'm leaving this as like an exercise to work out the maths, and trying to do the calculations yourself manually. It really gives you a very good intuition behind how it's calculated. So now let's look at with the negative correlation. Okay. So here, when X goes up, Y goes down. So we say this is a negative correlation because as X is going up, Y goes down. And you can see here, this is quite a strong negative correlation. So for example, one fundamental trading dynamic is called mean reversion, which is, we'll see this later, but just for now, just think of negative correlation, that if X goes up, then Y goes down. And then again, like here's an example of a perfect negative correlation, but in practice you'll never see this. So now we've just got a good understanding of the basic statistics needed for time series analysis. So now we can look into time series. And what I'm going to do is I'm going to, maybe if I just take this. Okay. Okay. So I just created some data. So this is data for Bitcoin dollar, the perp contract. It doesn't matter too much what the actual underlying instrument is. And this is a time series, and it's got, like, for example, here it's got an index, and this is like an hourly time series. So each row represents an hourly interval, and this is pricing data. So, for example, this is a very common time series, open, high, low, close, and then you've got volume as well. So with this time series, I just want to show some characteristics. So one of an important, let's just look at the plot first. So I'm just going to plot the closing price as a time series. Okay, so we can clearly see, like, there's like a trend here that's going up, especially like from 2003 to now. And what we want to do is I want to plot the histogram, or the distribution of the close price. And I'm just going to copy and paste this code here. And you can see here, this is the distribution, and essentially what it's doing is it's counting how many, like, this is like interval, like the range, right? So it tells us like how many occurrences at the particular price. So price is on the X, and then the frequency is on the Y scale. So you see here, like, but the problem with this is that there's multiple peaks. And it also doesn't make too much sense. For example, if I look now at I want to look at the central tendency. So I want to look at the mean, essentially. Okay, so I'm just going to see what the central tendency is. So it's telling me that the central tendency is around this $52,000 mark. So roughly around like here, but it really doesn't make that much sense, because this is not like you can see visually, this is not a central tendency. If it's a central tendency, it would be the highest peak. And really, you can see, like here, the highest peak is just below the $20,000 mark. So, and also if we have a look at, let's have a look at the dispersion, and it's probably going to be huge. So this is what we're going to do now. Okay, so there's a standard deviation of over $29,000, which is huge, right? And that's because if you just look at the range of the prices here, so this is why, say, in econometrics, they don't just analyze the prices, you analyze the returns or the differences. So this comes into the next section, differencing. So we want to take the difference in the time series, and when we do that, you'll see now if we plot the distribution. Okay, so maybe I'll just go over this code, what it's doing here. So I'm creating a new column, and it's called closed delta. And I'm saying closed delta equals the current close price, which is here, against the previous close price. So actually, just maybe if I make it even really more concrete, like what it's doing. Maybe if I just do this. If I take the closed delta lag, if I call it closed lag 1, okay, and it's basically this. And now I can just say that I want to take the difference between this, and then this will be a bit more intuitive. Okay, so you can see here, and it's really good to model the closed delta as well, because we're more interested in, rather than just the absolute the price, we're more interested in the price movement, and so when we predict this, it's either going to be a negative or positive number, and you can see here that this is, like, for example, this is how it does the calculation. It's close minus close lag 1, and you can see like it's moved down by $90, right? And now if we look, now what we're going to do is look at the distribution, or the histogram of the closed delta. That's the closed delta. Okay, and you see here now, there's only one peak, so this will be the central tendency. And so now what we're going to do is to calculate the mean and the standard deviation. So what this is telling us is that the expected, and this is more usable because we know that there's only just like one peak here, and this is like, by taking the difference, it makes it more of a statistical distribution, and with just like one peak here. So the peak here is like saying it's on average it moves by $2 positively per hour. And we can also now just look at this, the standard deviation, and we can see that the standard deviation is way much lower now. So rather than being like over $29,000 standard deviation, it's just 334. So yeah, and by looking at the price movements, you can analyze, like, okay, like what's the probability of it going up by, let's say, $100 or $500. But yeah, and the one of the key things though is this concept of stationarity, because in a lot of textbooks you'll see that they'll say that by taking the difference, you're making it stationary. And I'm just going to go over this concept of stationary versus non-stationary. And this is quite a controversial topic. And then, oops, maybe put that as a text. So essentially what stationary means is that the statistical properties of the time series are constant over time, so they never change. So for example, more concretely, so for example here, the mean never changes, but and there's quite a lot of textbooks that say that if you take the difference, it makes it stationary or weakly stationary, and it doesn't necessarily mean like, so for example, I'm going to just show an example, just empirical evidence that if you take the difference, it does not make it stationary. So for example here, and I'm going to print out yearly stats. So you see here that I'm just grouping it by year, and you can see that the mean and the standard deviation are not constant over time. So this, you could say this is weakly stationary, but how do you quantify weakly stationarity? But the key thing here is that even though if you take the difference, it makes it more predictable, but doesn't make it necessarily more stationary. I think that's maybe another video for itself, but yeah, so just bear in mind that if you take the difference, it doesn't make it completely stationary. It still can change over time. And so yeah, so that's the concept of non-stationary and stationary. I actually will maybe put a link, because there's a very good article about stationarity non-stationarity, and memory. And it's some really good arguments and also some code to back it up. Anyway, so that's now we need to go into lags. Okay, so what we'll do is we're going to take the closed delta and we're going to create what's called lags. So it's very common in econometrics and time series analysis is you want to predict the future values in the time series from the previous known values in the time series. So we want to predict essentially closed delta, and we want to predict it from the previous lags. So this is lag 1 represents the previous hour, lag 2 represents the previous second hour, third hour, fourth hour, etc. So we're going to run this, and so now what I want to do is just to print out and just show what it's actually doing here. So you can see here that we want to make it like all the data all in one row. So for example, this value here corresponds to this value here because it takes it from the previous value and so forth, right? So like on lag 2, it takes it from lag 1 and so forth. But in practice, we want to remove all these null values or NaN values, and the way we can get rid of them is by this drop NA. Because when we pass it into the models, actually some models, like for example gradient boosting trees, they're not sensitive to nulls or NaNs, but linear models, neural networks, they're sensitive, so we typically remove these out. So now we've dropped, let's say, the data. You can see like here, this is like the first row, there's no nulls at all. So we're going to go into another topic now, which is serial correlation. And serial correlation is looking the correlation between the values in the time series. So more specifically, we're going to be doing this. So we're looking, so don't worry about these values, so just look purely on these values here. So you see here that the correlation between lag 1 and closed delta, it's a negative value. Okay, so that means when lag 1 goes up, then closed delta is a negative, will go down, and vice versa. So if the lag goes up, then this goes down. And an interesting observation is that this correlation decays over time. So you see here, this is like 0.01 and then 0.007, and you see it decays slowly. So this tells us that the strongest correlation is from the previous value. So, and this is sort of like models what's called like mean reversion. So if mean reversion is essentially if the previous value is down, then it's more likely to go up, and vice versa. And that brings us to this concept of called auto-regression. Okay, and we're going to just be there's several models of auto-regression, and we're going to be focusing on what's called a first order auto-regression or model. Because this is quite a long-winded name, it's abbreviated to AR1, and I'm just going to explain what this is. So imagine I've got a time series and it's log returns. So this is our time series of log returns. And you know from the previous returns, essentially the returns put in log space. And by putting them in log space, then they become additive. So this is the time series of log returns here. And you can see it's hovering right between positive and negative, okay. And so what we're going to do is we're going to look at the first lag, and then that's essentially what auto-regressive does, is like making a prediction from the previous lag. So what we're going to do is from this lag is to predict the log return. So this will be our model input, and this will be our model output that we want to predict. So we're going to model the relationship between the log return and the log return lag 1. And the model definition, or the maths of AR1 is the following. So I'm just going to say, we're going to say that Y is our TS log return, okay? And Y lag 1 equals time series log return lag 1, okay? And we also have a weight, and we're going to put that to 0 just for now, and also a bias. So this model only has 2 parameters, and we're saying that we're going to model the relationship between Y and Y lag 1 as the following: is the weight multiplied by Y lag 1, so that's the previous value, plus a bias. And so, for example, if the bias is going to just bias the prices by a certain amount, so just imagine like if the weight is 0 here, then it's essentially that Y is just going to be the bias. So that's the model definition. And the reason why econometrics, or this model, is very powerful is because A, is its simplicity, but because it can model the 2 fundamental trading dynamics. And now we can go into what they are. So the fundamental trading dynamics. And if you've done any trading yourself, you probably know what these, I think they might be called patterns, or I'm not sure what they're called. And this is essentially, maybe if I add another text, the first one is mean reversion. And then the second one is momentum. And essentially, mean reversion is essentially modeling what comes down must come up, and what comes up must come down. And momentum is like what goes up stays up, and what goes down stays down. And this is like the if you axiomatically broke it down, then this is like the 2 most basic trading dynamics. So now we're going to look into just mean reversion first. Okay, so what I'm going to do is like let's just say in the next video I'm going to go over how we calculate these weights and bias, and this is essentially what's called like mathematical optimization, because you want to mathematically choose the best optimal parameters for the weight and the bias. So we're just going to say here the weight and the bias, and I'm just going to give you like a very small epsilon here. Epsilon's essentially just a very tiny number. And we're going to say that Y hat, so Y hat is our prediction of Y. So this is the actual value of Y, but we want to make a prediction, so we denote it as Y hat. And we're going to say, and essentially just regard it as our prediction. Okay, so it's going to be the weight multiplied by TS log return lag 1 plus the bias. So now this is our prediction, and now what we're going to do is just to print it out. Okay, so you can see here that if we look at our model, input to our model is this log return lag 1, and wants to predict log return. So we don't know what this is. So we always know what the current value is, and we want to predict the next time step. Okay. So and you can see here that it models it quite well, because you can see, like, if we look at what's called the directional accuracy, which is essentially just looking at the sign of the return against the predicted against the actual, you can see they're both like positive number, and you can see here that this is a negative, so it's moved down, and it's predicted correctly that it's moved down, and exactly the same here. So it's predicted that it's going up, and it has actually gone up. So obviously this is a toy example, but this is just to emphasize this mean reversion behavior. So this time series is reversing around a mean, hovering around roughly around the 0 mark, right? And just with this basic model, we can model mean reversion. So that's the first like trading dynamic, and the second trading dynamic is the following: momentum. Oops, I'm going to put that as a text. And so with momentum, what I'm going to do is create a new time series that exhibits momentum behavior. So you see here that if the previous log return, it seems to be like consistently going up, and then it goes down. So and then if you look at the lag, so what we want to do is predict the log return from the lag. Okay, so and what's very important is that extremely important is the how it models it as the weight is a negative number, so it inverses the sign of the lag. So if the lag is negative, then it inverts it to a positive and then adds a bias, right? And this is where the mean reversion. So with this AR1 model, that if the weight is negative, then this exhibits mean reversion behavior. So that's a very important note, is the weight interprets the trading dynamic. So now we've got the log return. So now what we're going to do is look. So let's just say we've done some machine learning or some form of mathematical optimization to work out the most optimal weights. And now let's say, notice here that the weight is positive now. So it's essentially saying that this the predicted future log return is by essentially like a positive decay of lag 1 plus some bias here. So let's have a look and compare it. So we look at lag 1. Because the weight is as a positive number, and it stays positive here. So and you can see that it's predicted correctly. Okay. And it has done for the several, but when it actually starts to change the momentum, maybe like a regime change. So regime change is like essentially the statistical properties change, and now it's like going down. Okay, so the first one here, it predicts incorrectly, but you can see from the following ones, you can see here that it's predicted it to go down, and it actually has gone down. And for example here, it predicts it's going down, and it has gone down. So this is how it models momentum. So if and again, the weight really interprets if it's mean reversion or momentum. And that's the end of the video. So in the next video, we're going to go over, so the next video is going to be matrices. And we're going to, so essentially matrices are two-dimensional arrays, and this is sort of the heart of machine learning. And so we'll learn some linear algebra as well, and then we can actually start to do some machine learning. And yeah, and please like and subscribe, and I'll see you in the next video. This course is free thanks to my paying Patreon supporters. If you're getting value from this series and want to help me create more, please consider joining them on Patreon. You can also support me by buying me a coffee on buymeacoffee.com. Links on my channel details page.